Okay. Hi guys. So my name is Max. I'm one of the SIs for Dr. Maduro's BIO005A lecture this quarter, and I will be going over the first SI video. So in this video, we're going to talk about cell theory, a little Chem 1A review for you guys, intermolecular forces, and I'm going to use water as a model for that. And then I'm going to talk briefly about pH at the end. And I also wanted to include all of the SI leaders' times, as well as our names and when our meetings, or how you can get to our meetings. And so that information is all there if you already haven't been to an SI session. This is also posted on Dr. Maduro's Isler page. So the first thing is cell theory, and there's three main topics that you guys need to know about it. I'm gonna say these in very layman's terms. So in the first one, all organisms need to be made up of some kind of cell, right? So either you have one or multiple. One cell organisms include bacteria, things like that. Multicellular organisms include things like humans or more macroscopic life that you'll see. The other thing is that the most basic unit of life is a cell. That means anything that we will consider living is going to be built by cells and built from cells. Lastly, all cells need to come from a previously existing cell. So that means, some kind of cell replication, cell division, stuff that we'll get into later on in this class. Okay, so for this class, the elements that you guys need to know are carbon, oxygen, nitrogen, and hydrogen, right? So there's four. These are what build up pretty much the entire biological kind of chemistry, right? So you guys have heard of OChem. All of OChem is built on these kind of four elements, right? Sure, you'll have like different ones, halogens and things like that thrown in there. But for the most part, a lot of what's organic, a lot of what's alive is built on these four elements. Okay, so this starts the Chem 1A review. I just want to talk about atomic symbols really quick. So if you have an atomic symbol, we have helium over here. The top left corner, this is the mass number, and that refers to the number of protons and the number of neutrons combined, okay? The atomic number, this is the bottom left corner. This refers to the number of protons that we have, and this is a special number because it determines what atom we're actually working with, what element we're working with, right? If you change the atomic number, you change the number of protons, you change the element altogether. So if I, for example, added another proton to helium, if I made that atomic number 3, for example, we would now be working with a totally different element, right? So that's the one special number. And then charge, it's in the top right corner. This is when you have a difference between protons and electrons. So remember from Chem 1A, protons have a positive charge, electrons have a negative charge. Typically, those two will cancel out to end up in a 0 charge. And so in a neutral element, you'd expect a charge of 0. But in this case, we have a charge of +2, which means that we have 2 more protons than electrons. And so at the end of this presentation, I'm going to go over 3 problems from the SI worksheet. And so if you want to get the rest of those problems, you would have to go to an SI session. We will also be posting those at some point on our iLearn pages. But I will be going over those problems, so keep these things in mind so you can kind of test your knowledge there. Okay, so the next thing is decay and half-life. So there's different types of decay, and I just listed them here for your knowledge. You don't necessarily have to know them for this class. What they really do is that they change the properties of an atom, right? So they can change the number of neutrons, number of protons, number of electrons. For example, alpha decay is the loss of 2 protons and 2 neutrons. That would totally change what element we have, right? Because if we change the protons, we change the element. So things like that can happen with decay. Specifically to bio and Dr. Maduro's case, he talked about half-life. And so half-life has this very loose definition. It's just half of the substance to decay, right? And here's this equation that's it's not labeled the same way. It's not one of those T1/2, T something, right? this is a bit more, it's like a colorful little like equation. It tells you how much you have at the end, how much you have at the beginning, and then you multiply that by 1/2, raise it to the time that's elapsed. So let's say 60 years, 100 years, 200 years, whatever, and then the half-life, which would be given to you in the equation. And this will also come out on the worksheet. So next we have electron orbitals. So remember that the different orbitals that we have the S, P, D, and F orbitals. For this class in particular, and most of the intro classes, you're only going to be dealing with S, P, and D. And remember the shapes of them, right? So the S orbital is a sphere, P orbital is like a dumbbell, and then the D orbital is like two dumbbells kind of crossing, or a bunch of different shapes there. Also remember how many electrons they have, or they can hold at most. So the S orbital can hold 2 electrons, the P orbital can hold 6, and the D orbital can hold 10, right? So that's for the orbitals. In terms of configuration, you can refer to the figure on the right. So this is the Aufbau principle, which tells you kind of the order where you should read this. So I wrote down it should go from S, then P, then D, then F. And that is the case in most times, right? You'll see that if we go from the top to the bottom, if you follow those arrows, you'll read everything as 1S, 2S, 2P, 3S, 3P, 4S, 3D, and so on, right? So make sure that you get in the habit of that. Okay, so intermolecular forces. Specifically, we're going to talk about van der Waals and hydrogen bonding as they pertain to bio the most. So van der Waals forces, these are temporary dipoles. And what that means is it's a random orientation of the electrons, whether they're on one side or the other, of an atom, right? So that's the very temporary positive on one side, negative on one side, and they're random, right? They're induced by something. So at any instance, all the electrons could be on this side of the atom, but the next second they could all be on this side, right? So that will change everything in terms of how they're all interacting. Lastly, for van der Waals, they're between nonpolar molecules. That's because polar molecules have a lot more stability between them because they have a lot stronger intermolecular forces. And yeah, so that's also because nonpolar molecules don't have a dipole, and that would mean that these temporary ones and these random ones can form whenever. Okay, the next one is hydrogen bonding, and I like to think of hydrogen bonding, it's being a specialized dipole-dipole. So that means you have an electronegative nitrogen, oxygen, fluorine, right? One of those three, and an H, hence the hydrogen bonding. So the need for an electronegative nitrogen, oxygen, or fluorine is because those three atoms tend to be some of the more electronegative ones. And they will have a strong interaction with a positively or a partial positively charged hydrogen atom. And if you want, your SIs can go more into depth with that. And I'm sure Dr. Maduro has gone in depth with that too. Okay, so I'm gonna again use water as kind of a way to explain some of this stuff. So for properties of water, there's 4 main ones. Again, there's adhesion, so that's water sticking to something else. Cohesion, that's water sticking to itself, so other water molecules. Surface tension, that's the ability for water to be so cohesive in a way and able to stick together. Then we have the high specific heat capacity, and that's just saying that water is able to take in a lot of heat before actually changing phase, right? So even in like a really hot day, you'll notice that it's not like the beaches all of a sudden dry up. They still have that liquid, they just get a bit hotter. And so notice how in this diagram on the right that these H's are partially positive and the O's are partially negative. That's because the polarity of the bond is strong, right? The oxygen atoms are a lot more electronegative than the hydrogen atoms. So that means the electrons will be around the oxygen atoms a lot more than the hydrogen ones. So like a magnet, right, minus attracts plus. And so that's why this partially positive hydrogen needs to be attracted to a partially negative nitrogen, oxygen, or fluorine. In this case, it would be oxygen because we're dealing with water. Okay, so before I go into the problems, I want to talk about acidity, basicity, and equilibrium. So for now, don't mind the thing on the right. I don't think you'll have to do hydroxide ions for now. In any case, you are more concerned on this leftmost arrow that deals with pH to H+, right? So that tells you the acidity, and the equation is there kind of horizontal for pH and for the concentration of hydrogen ions too. So acidity, that's how, acidic something is, and that's denoted by pH. It also tells you the concentration of H+ indirectly. Basicity, that's the opposite. So POH, that denotes the concentration of OH-. And Dr. Maduro should have shown you guys a equilibrium equation that he showed in office hours today. And he went over how water can be H+ or OH-. Okay, and so equilibrium, what you guys need to know about that is for equilibrium, you're gonna have a double-sided arrow, kind of what you see here on the right side. And so that means that the equation can either go to the right or to the left, right? And so it's relieving pressure. So if one side has a lot of atoms or a lot of molecules, you're gonna wanna go to the other side just because you wanna get rid of the pressure that's on this one side. So think of it like a bottle of Coke, right? So if I open it, I cover the cap with my hands and I'm shaking it, the inside of the bottle, think of the inside of the bottle as one side and this part of my hand and outside being the other side, right? So I'm shaking it, all that pressure is building up. So where does it want to go? Where does the Coke want to go? It wants to go out this way, right? So when I let go of my hand on one side, all the Coke's going to go out that way, right? So that's how you can think of equilibrium. And with that, I'm going to go to the problem set. Okay, so let's look at this first column here on the left. I think you guys can see my pencil. So first one is how many neutrons are there in a molecule of magnesium 24. So I drew out magnesium 24 rather poorly. Anyway, so remember that if we were answering this, you would first be asked to pretty much figure out what we have going on, right? So we have our two numbers here. So we have 24 and we have 12, right? So which one's which? So remember that our mass number is protons plus neutrons, right? And that's going to be equal to 24. So that's our top right corner, top left corner rather. And so that's going to equal 24. Our atomic number is equal to the number of protons we have, right? And that's going to equal 12. That's our bottom left number. So let me color code this so it's a bit easier. Say green. Okay. Right, so this is the atomic number, and then the top left is the mass number. So if you did some math there, you'll see that the mass number is 24. So I'm gonna kind of use the first equation, replace it with 24, right? The number of protons we know to be 12, given again by the atomic number. That leaves us with how many neutrons, as I denoted as N, right? So if you did some math there, you'll see that 24 minus 12 gets us to 12 neutrons. So that would be the answer for this. So we would say that there are 12 neutrons in a molecule of magnesium 24. Okay, so again, if you have any questions about these, please go to your SI sessions, any of the ones that are posted on there for Dr. Maduro's iLearn. And we will go over not only these questions as well as some more that we have a worksheet prepared for. Okay, so the next one, let's look at this column now. The second column. And so this deals with how many electrons are there in the outermost shell of silicon. So remember that the shells are the energy levels, right? So we have 1, 2, 3, that quantum number. Okay, so since we don't have a periodic table, I provided you this kind of caption here. So if I was answering the question, I would be thinking, okay, so silicon has an atomic number of 14. That means it has 14 protons. Since we have 14 protons, and we're assuming this is a neutral atom, that means we have 14 electrons, right? So we have 14 electrons to distribute to these different energy levels, right? And so again, I've ordered these in the same alpha principle way. So we go 1, 2, 3, 4, and we also go 1s to p, and then if there was a 4d, we would go to 4d, right? Okay, so let's do this. So we have 14 electrons. So I'm gonna bookkeep right here. Oh my goodness. 14. Okay, so 1s, remember that the s orbital can hold 2 electrons. So that gets us 2. So minus 2. This means we have 12 electrons right now. Again, s, so this will be 2. So minus 2, this gets us to 10. The p orbitals, these can hold 6, right? So that would mean we have 6 there, 2p6. 10 minus 6, this gets us to 4. This 3s, this can hold again 2 electrons, right? So minus 2. So that means we have 2 left. And so that would mean the p would take them both. So 2 minus 2, that gets us 2, 0. Okay, and the 4s, I just added that there. Okay, so you guys see now that we have 1s2, 2s2, 2p6, 3s2, 3p2. That's going to be our electron configuration for silicon. But remember, the question is looking for the outermost shell. So the outermost shell would be anything that has a 3. So everything that has a 3 falls within right here. And the number of electrons is actually denoted not by the 3, but by these two numbers right here. Okay, so that tells us that we have 2 plus 2, 2 in the 3s, 2 in the 3p. That means we have a total of 4 electrons in the outermost shell. 4 electrons. Okay. And lastly, this one's a bit more complicated, but this deals with the pH and the equilibrium arrows that I was talking about earlier. So which side of the equation will the buffer system shift? So if you increase blood acidity, think about what that means, right? If you increase acidity, remember that pH deals with hydrogen ions, right? So, and pH is acidic, or it deals with acidity. So increase acidity means you increase H+. And I can't do the superscript now. So you increase acidity, that means you're increasing H+, right? If you increase H+, remember that Coke bottle model. If I have a lot of pressure on my left side, right? So this, you can think of a lot of H pluses being right here on this side of the equation. And let's say there's like a given amount of space, kind of like the Coke bottle, right? If we have a lot of H pluses inside the Coke bottle, you keep adding H pluses, where does the system want to go? It wants to go to the other side, right? So to relieve pressure from the system, we move to the left side or the reactant side, right? And that's to offset the number of H+ atoms that we actually have. And so to answer the question, which side of the equation, we would go to the left side or the reactant side. And again, if you have any questions about these, please go to your SI. They'll explain it in more depth, as well as I would like to say 12 other questions from the introductory lectures that Dr. Maduro has covered so far. All right, thanks.